Okay, for lesson 9, we're talking about something called polynomial interpolation. So we'll define what that is, and we're also going to use systems of equations and matrices to help us solve initial value problems as well. So let's look at this polynomial interpolation. And what we're supposed to do with this is, one, if we're given some function f, construct what's called the interpolating polynomial. Two, once we have that interpolating polynomial, we can either integrate or differentiate it. So given some polynomial p, we'll call our interpolating polynomial p here. So given p, find either the integral of that polynomial, or we could, of course, differentiate it as well. And 3, the integral can be used to approximate the polynomial. So the integral from a to b, p of t dt is approximately the integral of the original function. So this is, in some regards, just another way to approximate a function or its integral or its derivative. And p prime of t then becomes an approximation for f prime of t. So these are some things that we can do with it. Clearly, this part 2 and 3 we can handle. It's this part up here, number 1, that's new, actually creating the interpolating polynomial. So let's see how we can do that. And this is easily done by example. So let's just suppose we want a quadratic polynomial. And here I'll just call it q of t, such that the graph of q of t passes through some specific points. And our 3 points are going to be 1, 2, 2, 3, and 3, 6. So these are just some data points that we have that we want our quadratic polynomial to pass through. So we want to fit a polynomial that passes through these particular points. So let's see what the general form is. The general form for q of t then, if it's just quadratic, it's going to look something like a plus bt plus ct squared. So then if we evaluate at 1, we know from this first data point, if we evaluate at 1, the output is supposed to be 2. So we plug that in. Q of 1 is going to be equal to a plus b plus c, and the output there is supposed to be 2. Q of 2 from the second data point now, if I input 2, I'm supposed to output 3. So Q of 2 would look like a plus 2b plus 4c, and again, the output there is supposed to be 3. And lastly, we'll take the 0.36 and run it through our function. So Q of 3 is a plus 3b plus 9c equals 6. And what results from this, I think pretty obviously then, is a system of equations. And it's linear, so we can do our normal routine on it. We would turn this into an augmented matrix, RREF it, augment, RREF, that matrix, and then we would grab the solutions off from there. Get some solutions, and interpret it in terms of the context of the problem. In this case, when you run all of that through, what you have is that A is going to be equal to 3, B is equal to -2, and C is equal to 1. So then we get the polynomial Q of t equals 3 minus 2t plus t squared. So this now is the quadratic polynomial that passes through those 3 points. And we could even see that if we jump over to Desmos. So let's take the points then that we have, put them on here. You see I've put them into Desmos already. So we had 1, 2, 2, 3, and 3, 6. And then what we went ahead and did is fit a polynomial through those points. So we solved for that. And there's the polynomial, that quadratic equation that passes through those 3 points. So you can see clearly that it does actually fit and do what we designed it to do. So that's the process of polynomial interpolation. And again, from there, we could do something like find an integral or find a derivative of that quadratic if we so desired. That's nothing new for us. We could easily do that. I don't need to show you that part. So let's jump back to the blackboard. And let's just generalize on what we've already done just a little bit here. So what we would do is, generally we would try and find the highest degree polynomial we could fit through a set of points. What that essentially works out to is you can make the polynomial of degree n if you have n plus 1 data points to work with. So I'll just draw out a quick table here. I'm going to put in a value for t and then a value for f of t. This will be t sub 1, t sub 2, t sub 3. We'll get a little dot, dot, dot action going on, and then a t sub n plus 1. And we have a y1, we have a y2, y3. These would be the outputs, of course, dot, 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 and then a yn plus 1. So we're trying to, again, generalize on the data points. So each one of these represents a data point. In this case, we have n plus 1 data points to work with. What that means from a more general standpoint is that we can create a polynomial of degree n out of that. So through the interpolating polynomial process, then we can create a p of t that would be a0 plus a1 of t plus a2 of t squared plus a3 of t cubed, and so on, all the way up to t to the nth power. So with, again, this many data points, we can create a polynomial of that size. So here's an example below for you to try out. In this case, I've given you 4 data points, so we can come up with a cubic polynomial to fit through those 4 data points. So give that a quick practice and see how that goes.